Hello, everyone. I'm extremely honored to be welcoming Dr. Aristides Patrinos. Dr. Patrinos is currently the Chief Scientist and Director of Research at Novim Group and also serves as the Non-Executive Director at Tsakos Energy Navigation Ltd, which is basically one of the largest independent transporters of energy. He has served as a Senior Vice President of Corporate Affairs at Synthetic Genomics and has also served as a Director of Biological and Environmental Research at the US Department of Energy. Dr. Patrinos is considered a leading authority in synthetic biology, genomics, global environmental change, and nuclear medicine. He's also considered a central architect in the genomics revolution. He was one of the leaders of the Human Genome Project and has been the recipient of 2 Secretary's Gold Honor Awards from the Department of Energy, and also the recipient of 3 Presidential Rank Awards. This interview allows us, the viewers, to understand the logistical difficulties behind the projects Dr. Patrinos has been involved in the entirety of his career, and how these projects shape the global and climate change policies. It's also an incredible educational/learning opportunity for the young generation to understand the sheer impact Dr. Patrinos has had over his half a century long scientific career. One thing I've been constantly thinking about whilst editing this interview is the part where Dr. Patrinos is talking about his involvement in Tsakos Energy Navigation Ltd, where he states that he partially did so to pay tribute to his maritime-rooted family. Now, this is a very simple statement, but serves to indicate his character and sheer love and care for his family and Greece. I want to thank him for kindly allocating over an hour of his valuable time to reflect upon his journey, share his life lessons, scientific expertise, and advice towards the young generation of professionals and aspiring students. I'm very honored to have you here, as I said, Dr. Patrinos. And I would like to start this interview from the period basically when you joined the US Department of Energy full time. So, how did you work at the Department of Energy, and how did your work got you interested into the genetic code?
Well, the genetic code came afterwards. My initial introduction to the Department of Energy was, of course, through the many national laboratories that I worked and did research in before I joined it. You know, the Department of Energy owns most of the DOE, most of the national laboratories in this country. Places that you may have heard about, like Lawrence Berkeley, for example, and Lawrence Livermore, and Los Alamos, and Brookhaven, so on, but it expanded beyond that. So I was fortunate enough, I came to the US in 1970, having finished the National Technical University in Athens, the Metsoviu. So, and I went to Northwestern University to get my Ph.D. in engineering at the time. But quite frankly, I always wanted to come to the US because of getting an advanced degree in a place where you can expand your horizons beyond the narrow focus of your PhD dissertation, for example. I mean, I became aware of the possibilities of doing a lot of very different and interesting things in the US, as it turned out. So even though I got a degree in engineering, I became aware of the difference in terms of the sophistication of the physical sciences versus the biological sciences. This is no reflection in terms of the quality of the work. It's just biology was treated in the research field as very much the best way to describe it, an observational or a non very rigorous discipline. It was phenomenological, that's the term to describe. Whereas in engineering, things were in the hard science business, where you used advanced sophisticated equipment as well as high performance computing. Those two concepts were pretty alien to the field of biology and medicine. So I completed my degree in engineering, but I was already pretty connected and very interested in applications of the information and the technology that I had acquired through the physical sciences for applications into biological and environmental applications. So once I started, I taught a little bit at the University of Rochester, but very quickly I joined national laboratories because those were the hotbeds of advanced research where you could mix it up with many other disciplines. You know, a national laboratory covers the waterfront of biology, of environment, of mathematics, of engineering, you name it. So within one place, you have the luxury of playing with all kinds of interesting toys. And I was sold to that. I worked at Oak Ridge National Laboratory. I worked at Brookhaven National Laboratory. While in those jobs, I also worked in other national laboratories. So at that time, the key issue that attracted me in research was the issue of global climate change. We were starting all to become aware of the dangers of global climate change, even though there was also considerable uncertainty. And there were very many people that doubted that that was a serious problem. So, but that was my first interaction in terms of devoting my time, the energy, and the knowledge that I've acquired, A, to figure out whether that problem was really as bad as people were saying, and B, how would we go about dealing with it in terms of fixing it? Because even back then, many years ago now, we were all aware and knowledgeable, I would say, and convinced that just by controlling emissions, it wasn't going to happen. You know, we, as humans, we are still very immature with respect to action, and especially in a diverse world as ours, the likelihood that we would all agree in terms of controlling emissions was pretty small. And I think that's becoming more and more true. So what's the alternative? The alternative is we have to come up with better technologies to fix this problem. If we can't control emissions, what else can we do? So one of the ideas that we had in those early days was, is it possible that biology can be advanced to the point where it can weigh in with respect to fixing the climate change problem? And beyond that, even the environmental sciences problem, the pollution problem, the fact that an expanding population like ours is going to have an impact. So there must be different tools and ways by which we can address it and fix it. So at that time, of course, you know, I became also aware that if you wanted to have an influence on something like this, it's probably important to try and get the position where you can weigh in at critical times with ideas and proposals so that you can address it. So that brought me the transition from a purely scientific research effort that was in the national labs to the Department of Energy that oversaw most of those labs, as well as had research programs. You know, the Department of Energy spends something close to $30 to $40 billion a year, most of it in research. So, and it's research, a lot of it is done in the national labs, but some of it is also done in universities. So we have big proposals, big budgets in some of these areas. And so that's one of the things I wanted to do. And I was successful in terms of getting into the Department of Energy, but also advancing within the biological and environmental research program of that department. that was in the Office of Science. So,
And your concerns led to the initiation of the International Panel on Climate Change and the Global Change Research Program.
yeah, I saw that in your notes. I was one of many people. I mean, the Intergovernmental Panel on Climate Change was an international effort, and it was driven primarily by scientists across many disciplines, in many countries, many walks of life, and so on. So to say that I had a major role, that wasn't true. I had a role, and I think it was a role that we pushed within the Department of Energy, because a little known fact is the Department of Energy, since it is in charge of energy, and most of that energy is basically burning coal and burning oil and burning natural gas and so on. So many of our bosses there were very skeptical about trying to control, because, you know, there's a private interest and so on. So it was a tough sell, at least initially, to get the political leaders, the political appointees in these departments, to buy into this notion that we're dealing with a serious problem and we need to deal with it. So that was the challenge also that got me into it. You know, there were many people who questioned me and sort of cross-examined me and so on. Some of them were secretaries of energy, some of them were, many of them political appointees of the various presidents that we had over the years. When I joined the Department of Energy, it was President Reagan who was there. And I don't know how much you know about him, but he certainly wasn't somebody who was very sympathetic to environmental reasons. You know, it's.
Oh, yes.
Although he came around and he recognized it was important. The subsequent one was his vice president, the first Bush, and, you know, all through all these presidents. The last president that I served was Obama, basically. I had already left the Department of Energy, but I came back in the last year because the then Secretary of the Department of Energy wanted me to help him with interactions I had built while I was still there with the National Institutes of Health. But anyway, that's jumping ahead.
You're talking about the last year, 2006, right?
Well, 2016.
2016.
Yes.
Okay, because I remember from looking at your bio that you left the DOE in 2006.
I left 2006 and started this company called Synthetic Genomics.
Yeah.
And then at 2012, I joined the NYU, you know, for urban science. You know, that's my. So anyway.
So, yeah.
So the first area of research that I took on full time was primarily the climate change problem. And it was an interagency program that we built. In retrospect, it was a fairly unique undertaking that was helped by the emerging systems of interactions and communication among agencies. For you, it's probably a little hard to believe, but in the early days when I was in the Department of Energy, we didn't have the internet. The internet was something very rare in the ARPA programs. So everything you did was telephones and fax machines and so on. So the different departments and agencies were pretty islands on themselves with very little interaction. So, and that was a different way of doing business, of advancing research and so on. So what we did with the US Global Change Research Program is a paradigm shift. At that time, the first integrated sort of coordinated program like the internet was not an internet, it was called Omnet. It was set up by oceanographers primarily, but it was the first time that we had various agencies various departments, communicating with each other through very primitive ways, but still being able to do it in real time. So you had a modem and you connected with it, and sometimes it took you forever to get on, but you were able to send a message that was communicated to multiple places. To you, it may sound something like, that's like a Stone Age and so on, but it was fairly effective. And it was the reason why the 13 agencies that were involved in the climate change problem, involved in the US Global Change Research Program, that also proposed and installed the Intergovernmental Panel on Climate Change, was those 13 agencies speaking to each other on a regular basis. It was a paradigm shift that opened the possibilities of communication and advancing research effectively and quickly for the first time. And that was where it happened.
I wasn't expecting the fact that it was basically one of the initiators of expanding communication. Because I was always looking at these projects at their core, what they're delivering as far as climate change, for instance, not what they have to do with communication mostly. So it's a very interesting shift that you're putting here, a loophole that I've never experienced.
Well, people your age,
I tend to forget.
This is like Stone Age.
Yeah.
When they see some of us,
we tend to forget.
At that time, we had 13 agencies, 13 groups of people that were working on this problem together. So you had to act quickly. You had to have a meeting, for example, set up relatively quickly. What did we do in the beginning? We would send faxes to, and the papers would jam, or we would call on the phone. You would call 13 different people. I mean, you'd run you couldn't say as much. So the ability to communicate quickly, agree, propose, and offer opportunities for review and adjustments and so on, because everything was on a very, very tight schedule. And in the government, especially on the science business, you compete with everybody else. And if you have original ideas and methods to implement and propose and advance your cause, you're more effective. And that was one of the reasons why we were effective with respect to the climate change problem. A lot has been written, and I've been asked to, I don't have time because I'm still doing some work, as much work as I can. But something needs to be written about it, and some of it has, but not as much as is necessary in order to learn from the past. So anyway, to make a long story short, I was focusing on the climate problem almost entirely. There were other parts of it, but I was within this program, this entity called Biological and Environmental Research. We had about 60, 70 staff members. So this program, as it says, it's the research in biology and environment. Environment was a lot of acid rain related work that I also had started at that time. That was the predecessor to the climate problem in terms of its importance and its impact. And on the other side was the biology. Now, it was very, very common when you were in the Department of Energy and you went and gave a talk about your biological and environmental research programs. People would say, why is the Department of Energy doing biology? It doesn't compute, basically. The Department of Energy is, talking about energy. So where's but everything has origins and evolutions that are kind of interesting. So it turns out the Department of Energy is the successor to the Atomic Energy Commission. Have you ever heard of the Atomic Energy Commission? AEC.
Yes.
Oh. So the AEC was created in 1947. I know that because that was the year of my birthday. Yeah. And it was created because it was right after the Second World War and the Hiroshima and Nagasaki bombs. So even though there was excitement and expectation that nuclear energy was going to do a lot of useful things, like energy or electricity too cheap to meter. That was an expression people were saying. There was also recognition that it caused potential effects that were deleterious to human beings and to natural things. So our predecessors of the time, the smart ones, started a program called Biological and Environmental Research because they wanted to explore, apart from all the benefits that nuclear energy will give us, will there be downsides? And there's no question that there are downsides. Of course, all the people that died in Japan, and since that time, all the effects of ionizing radiation on human biology have become very clear that there is a danger there. So the program was initially applied to trying to understand the effects of ionizing radiation on human biology. The tools that we used initially, I'm talking back in the 40s and 50s, were very primitive because biological research was also very much at the early stages. So what did we do? I mean, these are my predecessors. Those horrible things. You irradiated animals, put them under the nuclear ionizing radiation systems, and you looked at what would happen. And, you can just imagine the horrible things that were happening. And we thought, however, that by sacrificing these animals, we would learn enough to maybe solve this problem of dangers of ionizing radiation. So, and it wasn't just animals, it was also human beings that were already terminal in terms of their life, and they volunteered to subject themselves to a lot of radiation so that we can understand the mechanisms, okay? So lots of research, I'm talking about starting in 1947, well into the 60s and 70s and 80s. And the results—
How was then that knowledge channeled into the Department of Energy? How was that knowledge channeled?
Yeah, it was all in the Department of Energy. I mean, there was, of course, a major health-related research effort, which is the National Institutes of Health. But what we were mostly focusing was at that very, very narrow part of ionizing radiation on human biology. And what it became clear is we weren't getting anywhere. We were not getting anywhere. Of course, even though we were focusing on ionizing radiation, the whole office, at that time, I wasn't even in that. I was mostly on the climate side. So at that time, the information about biology, and especially about molecular biology, were starting to emerge. So by now you must know about Watson and Crick and the double helix and so on. Keep in mind that both of these guys are not as important as Rosalind Franklin, who is the one who, in fact, got the information about the double helix. These two guys stole from her. That's a side story that you should learn. And if you're in the UK, you should learn that because these guys did the work in the UK and stole the ideas from her. Anyway, that's a side story. Okay. So,
but a very interesting one.
Yeah, I mean, you should Google it and you'll find out a lot. Rosalind Franklin is the name of that woman. She died very young of cancer in her 30s, but she was the one who discovered the double helix. Anyway, we were aware of some of the medical applications and the biology and so on. So a long story short, this could go on for days, and we were convinced, and along with our colleagues in other departments, including biology, that unless we understood biological processes at the molecular level, at the double helix level, that we would never be able to find answers to what causes the damage from radiation. So, and that's when the concept was born that we could sequence the human genome. The 3 billion base pairs of human DNA. And once we did that, already we were aware of the existence of genes on the genome. We were sort of aware of what the genes did. For example, the genes coded for proteins, and the proteins were the ones that did the work. So, science was advancing, and initially was very primitive, but we started getting some ideas about what could increase our knowledge to the point where we can provide answers about what ionizing violet radiation does to biological processes. So, and also, and this is the point that I stress, is even though we were doing environmental and biological work in the Office of Science of the Department of Energy, okay, we were in the bosom of the physical science. All our other offices that spent a lot more money than we were spending at the time, high energy physics, nuclear physics, chemistry, engineering, and all these were big science approaches, as well as high performance computing. This is when we started imagining about supercomputers and what all this could be done, especially the machines that would hit particles together and discover the different parts of matter and what they came about. So we were beneficiaries of our coexistence with big science challenges and big science champions. NIH, the biology part, was separate in another agency, and they still had the small science mentality. They still have it, in fact, and don't deny that. It's just a matter of catching up that needs to be done. So we benefited because we were, have you ever heard the word chutzpah? It's a Yiddish word that means...
No.
I'm trying to think, there is a Greek word for that too. Sort of, you have you're
Maybe
sort
if you
of
describe it, I will be able
you
to.
have the nerve to propose things well beyond what the expectations are. By somebody, if you're not, for example, you have a very simple job, but you have dreams, and then you make a proposal about something, it's chutzpah. So there is even an English word, another English word that could...
Maybe proposing something preposterous, I assume.
Preposterous,
something
yes,
that's way beyond your reach at the stage you're now.
Preposterous is a good word. So our reaction when we started thinking about biology, in terms of effects of radiation on this biology, and then starting to understand the genetics, the structure. So we said, you know what, if we can sequence this damn thing, we may be able to get to the bottom of this connection between ionizing radiation and biology. I mean, it's to everybody else, including all the biologists, it was preposterous. Why? First of all, we didn't have the tools for it. And second, and perhaps more important for them, when we did some very rough calculations about what it would cost to do that, of sequencing the human genome. Interestingly enough, we weren't very far off in the final analysis. We said, it'll take about $3 billion. For us, it was something that we could propose because in the bosom of the physical sciences, the other departments, the ones that had the light sources and the neutron sources, that's the kind of money they were spending. So for us, it was understandable. So we can do it with $3 billion in 15 years. all the biologists everywhere were up in arms because these amounts of money were huge for their small budgets. At that time, and I don't mean it in a derogatory way, biological research was done in a small science way. You know, it was rare that you would have a team that was more than one principal investigator, maybe a couple of postdocs, and 3 or 4 sort of assistants. That was a big lab there. And what we were proposing was essentially something on the scale of the Manhattan Project. That's what we had in mind. You know what the Manhattan Project was? It was the
I can't remember the Manhattan Project.
The Manhattan Project was the project we put together during World War II to create the first bomb. And that's how we won the war. But it took a Manhattan Project, which means lots of labs integrated together, working together, you know, comparing something alien for biologists and also for science back in those days. There's an interesting movie that's coming out about Oppenheimer. You know who Oppenheimer? Look it up. It's coming out, and it's Oppenheimer is the person who, the scientist who was responsible for the first atomic bomb. So you can get a sense of that. I mean, I haven't seen it, but I know the story and everything. You can see the sense of the big teams that were organized to solve a particular problem. And so that was our conviction that if we would combine sources and the right kind of money, we would be able to do it. Where NIH didn't want to have anything to do with it because they were afraid their little programs were going to suffer as a result because they weren't well funded. Again, it's an interesting story by itself that needs to be written, and I don't have the time to do any more than what I'm telling you here. So anyway, the bottom line was we proposed it. The NIH didn't want it to happen. We pushed and pushed and got a few people, a few friends, politicians that were essentially forward thinking. One was a senator from New Mexico called Pete Domenici, who was our champion, you know, who understood what we were trying to do. So anyway, long story short, the two agencies agreed, NIH and the Department of Energy, to work together on the Human Genome Project, which was launched in 1990 officially. By that time, you know, I had been sold on making a switch and focusing more on the biology than the environment. But, you know, I didn't give the other one up. I was promoted when I had responsibility for both programs. So it was like a kid in a candy shop to have this opportunity to work on 2 very important projects that I mean, I wish I had more time and more hours in the day, more minutes in the hour, and because everything was happening so fast and the excitement was unbelievable. So that was what eventually, you know, especially the decade of the 90 to 2000, I did nothing but the Human Genome Project. And that was one of the most wonderful experiences I've had, both in terms of the output, you know, the result, and what it could be used, especially given today's advances. I mean, those days we kind of only dreamt of those. And to see that happening was unbelievable. Now, it was tough also because we weren't sure that we will be successful. We're talking about sequencing a genome that had 3 billion base pairs. So you're an engineer, you can, you know, do some calculations. When we started in the beginning to get our arms around how we would go about doing that but we could do it. We could sequence genomes, but it was costing $10 a base pair. Okay, $10 a base pair. So we're talking about 3 billion base pairs So just as the first number that you come up with is $30 billion. It was no way that anybody would be able to do something like that, especially back then. So we were learning, but we were faced with some impossible odds in terms of closing this. And it wasn't just the cost, it was also the culture. I mean, I'm referring to, I mentioned about the labs back then. A big lab at NIH was very few people that worked together. They did wonderful work, but they were very separate from, another part of NIH that worked on heart disease, another one that did on aging. All these things were little, it was just that kifinis, small groups together. Whereas what we were proposing was something that needed to be done as a team, a large team. And that was a paradigm shift in the culture. And so that was one of the very attractive parts of taking this on and pushing it, convincing people that it was worthwhile, not just in terms of the final outcome, but worthwhile because it was possible. In the beginning, even the very smart people thought that was impossible. You can get a team so big, organized in such a way so that it can produce something within the time scale that we had planned and proposed. We said $3 billion over 15 years. So anyway, as I say, the rest is history.
How did the project reframe your mind as a scientist? Yeah. How did the project reframe your mindset as a scientist?
Well, I mean, for us, it was easier. That was one of the reasons we had the chutzpah or the preposterous attitude, that because our colleagues down the road in the next lab, who were physicists, physics is, of course, something that was around much, much longer than we have. And the people that made the big advances in physics in terms of, Einstein and all the successors, and they were used to working as big teams. They were used to working with big toys, big machines. So we had that knowledge by proximity, even though we were in the biological and the environmental field. They were next to us in the same labs. We used to use some of their equipment sometimes, or we would see possibilities of collaboration here and there. So for us, it was more a natural thing than for the others. We were preposterous in terms of pushing it. But sometimes it takes that kind of thing. And it wasn't easy, and it was not smooth sailing. I mean, we met tremendous opposition by the establishment of the biological sciences, prominent people, terrific scientists, physicians, all these people that had a certain way of thinking that was not amenable to the kind of engineering project that was sequencing the human genome. To them, it was the hypothesis-driven science, which was the heart of biological science, and still is to a large extent. And I'll explain it this way. You have a small team, the scientists with a few technicians, and what you think about some problem that you want to solve. So you propose a simple problem that you want to solve, and then you develop a proposal about how you go about solving it. In terms of taking a few measurements, doing a few analyses, thinking, and you propose it. And you get funded after a review, you get the money, you go ahead with your little team in your lab, you do the experiments, you either confirm the hypothesis that you pose, or you don't. If it's not confirmed, then you think up of something else, and you do the same thing process. If it confirms, then you think about the next step beyond that hypothesis. What's the follow-up? And to do the same thing. So science across the board advances slowly, but across, across an entire field. And knowledge improves that way, and it did, in all those. Whereas what we wanted to do was a disruptive way to get to something, because we said if we sequence the human genome and understand all the interplay of the genes and the proteins and so on, we would be able to harness that knowledge to solve the problem of heart disease, or cancer. So we were
the applications
way into the future, and we were thinking about an advance that it wasn't possible at the time. I mean, whereas the previous one that I would say that advanced, you knew what kind of experiments you would do. They were very simple experiments of mixing this and that. And whereas we said, well, we will have the genome, and once we have the genome, we'll do that. But how were we going to get the genome? I mean, it was 3 billion base pairs, and we didn't have $30 billion. It wasn't possible to do that. So we were preposterous in terms of proposing something that was very alien to the biological thinking. So, and at that time, there was no guarantee that some of the methods that we were thinking about developing and so on, that they would work. It could have taken much, much longer, in which case maybe the funders of these program would give up on us because it was taking very long. But we were convinced. I mean, I certainly was convinced that if we could channel the collective energy of these armies of people that could do this, then it would happen. It's like, well, the expression that we would use is like shit happens. That was the expression.
Shit happens indeed. I can add. And I mean, you're talking about the project as if it would be more successful if it was to be developed now in 2023. Would that be the case? Do you believe it would be more successful if you started developing it now?
If we did it developing now, if we hadn't done this advance, of course, because all the tools that we were harnessing were being developed, quite frankly, independent of us in the field that we were in. For example, the best example is high-performance computing. That was one thing. If for whatever reason we didn't advance scientific computing, this would not have happened. The principal reason why this program was successful was because we not only took advantage of it, but we harnessed it. And we had to do it in some ways that were bizarre. I mean, I'll give you one simple example. At the time, scientific computing was advancing, but it was advancing in all these other fields. Physics, nuclear energy, nuclear physics, high energy physics, chemistry. All these fields were taking advantage of high performance computing, except biology. So because nobody could think of a way to use biology. We had, as I mentioned, we had these small labs, and you were focusing on a small lab with a simple experiment. You did an experiment and you proceeded, but you never needed a particular one. I had an oversight in my program, and I wanted to get biologists more involved. I would bribe people to use high-performance computing in biological problems, to do it to me as a favor, because that way I could entice the broader community in biology to get interested in scientific computing. I think personally that scientific computing was the principal reason why we were successful, because people put 2 and 2 together and they could see the benefits of having this new powerful tool that up until that time, everybody thought it was just the high energy physicists that wanted that, and why would we use it in biology? So, and then of course, once you did you had all the other tools that you came about, capillary electrophoresis, which was a method that was used in chemical sciences, was at the heart of the sequencer that was developed. It was a very simple, with our standards, with the physics, with the science of the time. But for biology, it was unprecedented. The biologists didn't even know what it was. It couldn't even spell it. Capillary electrophoresis. All these things came about because there was the motivation, and there was this chutzpah that I mentioned to push. So, and the rest is history, as they say. Although, it wasn't an easy, we're talking about a process that took certainly 10 years. And there were a lot of highs and lows. I mean, there were highs, of course, when we made progress, but there were also lows because the culture had to be changed. And there was tremendous resistance from established communities, scientific communities, not wanting to change. So there was sabotage occasionally, it was human imperfections. I mean, we are, after all, unfortunately, very imperfect as human beings. So it was manifested also in our pursuits in research, and that was but we managed. And there was a lot of rivalry, of course. Once things started happening, so to speak, when people started getting the sense that, hey, we may end up succeeding. For most of us, it was the journey. Even if we didn't succeed, we were not going to feel bad. We were going to move on to something else. So when things started looking like they would succeed, then you get all kinds of other associated problems about rivalries and how to take advantage of it, how to capitalize it, how to compete, and so on. So
do you believe your
at that time, the other story
will overshadow? Yeah.
So say that again.
Do you believe? Yeah. Do you believe that your contribution in the Human Genome Project will or overshadowed everything you did after that?
No, I mean, there's still so much excitement. There's still so much to do and so many uncertainties. I mean, I'm not a medical doctor, but as a result of all the research that I've done, I mean, I'm aware of, and as I get older, of course, I'm more and more aware of how finite our life is and how little we know about medicine. I mean, we've done tremendous advances, but we still haven't really extended life all that much. In fact, in many ways, we have reduced it because we've polluted the world. So no, there's still so many things that could still surprise us in the benefit in an important way. But I was about to say, it was around that time when I mentioned scientific computing and so on that the rivalries started happening, and the fact that we saying, oh shit, we may succeed here, and then what happens next? What's going to happen? Well, then you get all of the competition that emerges from success. So you want to take advantage of it any way you can. And so I bring it up in terms of the private program that was created, to compete with the public program. And that was the Celera. I don't know whether you've read about that at all. Have you?
No.
So, I mean, the public program, at that time, of course, we had incorporated also the UK. It was primarily in the early stages a UK and a US program. I pushed and also got China involved, and then we got Germany and Japan and so on. But it was a publicly funded program across the world. The two major ones were at the time the US and UK. The US much bigger. I mean, the US, for example, I'll give you one. in the end, we agreed to create 5 major centers to do the sequencing ultimately. 4 of them were in the US and 1 of them was in the UK. That was it. And we had little programs here and there in China. I pushed because China was the biggest country in terms of population. So here we're talking about a program that's supposed to help humanity, and we were ignoring a large part of that. So now, of course, the relationship with China is deteriorating again, but that's a different story. So where was I? Yeah. So while we were proceeding, it was essentially a publicly funded program. Publicly means it was funded by governments, and therefore the benefits of that research will have to be broadly available to the world. That was the concept. Of course, you know, in the UK and the US, we have the private sector, and now we have it across the world too. So there were initiatives on the private sector that wanted to also get involved. And in their particular case, you know, they would want to, for example, take advantage. If they devote much effort with their money, for example, then in the end, if they're successful, they deserve to get some profit from it, right? I mean, it just makes sense. Mm-hmm. So it was inevitable that there would be a public versus private rivalry. So such a rivalry, and that's another big story that's taken many, many books, and I was involved in both sides of that as well. So there was a company that was created in the US called Celera Genomics. And it proposed to sequence the human genome on its own with techniques and ways that were different than the ones that we were following and advancing in the public side. So eventually what started as a, you know, kind of seeing each other, it ended up competing with each other about which program would finish first, and if the private program would finish first, and if it could sort of get all the intellectual property and all that information for its private use, and then it will make huge amounts of money and perhaps wouldn't share a lot of that information across the board. So it was a natural thing to create a public versus private. I mean, I ended up playing a role in both of these programs. I knew the person very well who had started the private effort. And I saw ways by which those 2 programs could work together and help each other as opposed to compete. And that was the final stages of this which turned pretty ugly because the 2 sides were very much at each other's throats. They didn't agree on the way to go forward, and they didn't want to share. It was pretty ugly. And the downside for us in the public program, especially in the US, but some of it in the UK as well, was that the private sector in the US, understandably, were asking, why are we funding with our money, the public money, this program when the private sector is going to do it all by itself? So there were a lot of people in the government in the US that weren't sympathetic to our doing this particular program, especially if the private company was going to do this anyway on their own nickel, as we like to say, with their own money. So it became entangled and complicated and ugly. And whereas this was something that was one of the most important research efforts that humanity ever undertook, and I'm not exaggerating, you didn't want to have that turn ugly. So perhaps the most important contribution I've done is to bring the two sides together and get them to agree, so that at the very least, we wouldn't kill each other, or agree at some level that we can maybe not collaborate to the extent that I would have liked, but at least tolerate each other and have a more, I would say, collegial partnership, or collegial
humane approach on the cause. Put the cause above bigger conflict.
Collegial, and it happened. I mean, that accomplished.
Mm-hmm.
And the person who led that private effort was somebody who I knew over the years. And even though I was leading a program that was competing with his, at the personal level, we were friends. And we would share information, but without taking advantage, so that we wouldn't take advantage of information that we shared, because we were friends. So, and I had tremendous respect and admiration for him. He did make some advances in this field that were pretty pivotal in the ultimate success of both programs. So, I know many of my colleagues in the government, of course, hated his guts and still do. But I found the final outcome and the interplay to be very constructive and useful. To the extent that I was tempted then afterwards, after we finished this program in 2003, to the extent that we could do anything. I mean, the advances still needed to be made, but as a group effort, it pretty much finished in 2003. So that's when I left a couple of years after that, because Craig, who was my colleague on the private side, had moved on beyond reading the genome to writing the genome. And that's the sort of synthetic genomics. I don't know whether you've heard this, synthetic genomics. Yeah. This is a case of not just reading the DNA, but building it. And perhaps if you build DNA, then you can create life, if you want to be dramatic about it. And so we started a company together called Synthetic Genomics, where we were dreaming. I think ultimately some of our dreams will happen, but they didn't happen on the time scale that we wanted. So ultimately we drifted apart and went. But advances are still being made in terms of now synthesizing DNA. Well, you can create life, or synthesize the DNA piece, and you can stick it in a cell, and you can have it do things that it wasn't doing before. You can then imagine ways by which you can solve problems, for example, like the climate change problem, in ways that we hadn't thought about before, and in ways that you perhaps don't have to sacrifice too much with respect to natural resource. For example, if you can re-engineer life in ways by which it can sequester the carbon in CO2 and other emissions, for example, and convert it into other useful products. Biology can do that, theoretically. It's just you have to have the right kind of tools to proceed. So many of these ideas that are harebrained schemes at this, where are realizable. I may not see them in my lifetime, but I think you will see some of those that are going to be unbelievable in terms of the applications. So, and the most recent thing that's important to mention, I mentioned, what we did is we read DNA. And then we made some advances in synthesizing DNA. But the latest, in the last few years, Jennifer Doudna, I don't know whether you heard the name before.
No, I haven't heard the name.
So what she did, which was the next big step, was editing DNA. So it's called Cas9. It's a understanding, again, molecular biology to the point where rather than synthesizing, which takes a long time, and sometimes you can't synthesize it well, you can edit DNA. And you can edit now with a fine-tooth comb. And you can take the DNA and you can go anywhere in it and change a C to a T or an A to a D, or all these things. And you can do it a lot more effectively. So editing DNA is now this big next stage. I'm involved mostly at the peripheral, at this field has even advanced well beyond where I'm at this stage. I rejoice and I vicariously dig this big way, but I no longer do the kind of things I did 20 years ago.
So if you take two of your biggest passions, which is the first thing is energy and the second thing is genomes, and you put them together, how did you transfer your decade-long experiences, basically multiple decade-long experience, into the Tsakos Energy Navigation? How did you
Well,
support
Tsakos Energy Navigation was a side thrill. I mean, of course, I'm Greek. I don't know whether you know, but I was born in Egypt of Greek parents. So
yes, in Alexandria.
My ancestors come from the island of Chios. So esis paleolithites.
Really?
So both my grandparents, my grandfathers were from Chios. They were both sailors. They both had in the merchant marine, basically. So
you had to basically go into the maritime industry.
Well, I mean, I was only in Greece for 5 years doing my undergraduate at Metsovios. That's Metsovios. But I was Greek, of course. When I was in Egypt, it was the Ambetio Scholi was one of the best schools that I ever went in. So I was educated in Greek, and I had friends and family in Greece. And of course, it turns out, being Chiotis, the Tsakos family is from Chios.
Yes.
So, the father of Tsakos, Panagiotis Tsakos, he's the person who started the big company that he had, was also, and is also still, I mean, he's well into his 80s. He may even be 90 now even. But he was also a very interesting person, very curious about things. And so he followed what was happening on the human genome. And when he found out, and that I was also from here, so he invited me, asked me to give a talk and so on, and one thing led to another. And he asked me whether I wanted to be on his board. So what's not to like? I get to go to Greece 3 times a year, and it's a very worthwhile activity. It's what sustains Greece in many ways. And also it's a place where some of the applications could see benefits from some of the science that we've advanced. So what's happened since I've joined is we've done a lot of possibilities in terms of using renewable fuels, in terms of using molecular biology or biological advances to decarbonize fuels. So there are obvious applications of some of the tools that we developed for other reasons in an industry like shipping. So
and Dr. Patrinos,
and also my grandfathers were all in the shipping business, and my father was the first in a long line of Greeks who didn't want to go to sea, and he didn't want us to go to sea too also, which I don't blame him. I'm grateful for that, but in some way I wanted to give back to the ancestors who were perhaps disappointed that we didn't follow the chain of running a merchant marine industry. So there you have it.
Dr. Patrinos, it's what can I say? It's an ocean of knowledge. And for me to be able to be tangentially connected
Oh, come
to the
on,
universe of
George.
somebody behind this project, I mean, I have to say, I'm a young guy. And in this friction, I'm very curious as well. Maybe not to the level of Mr. Tsakos, but I'm very curious. It was always a dream of mine to be able to talk to people like you and to understand what's going on. And the possibility of that happening, I didn't know what the possibility was. And now that I can realize that by talking to you, it's incredible. It's incredible for me to be able to
Oh, I'm glad.
discover what
I'm glad.
happens on the backstage, behind the pulling the veil, behind the name of the project, what happens with the logistics of it. And now I know. And this makes me very content for the future, to have knowledge. And I believe that a lot of other students who will see this interview will resonate with me because I believe I'm the medium of transferring all that to other young people who want to know more. Because at the end of the day, you cannot talk to thousands of students. You can only talk to selected few people.
You are most gracious. But
and you gave me more time than I asked. It's been an hour and 10 minutes, and I could keep you here for way longer than that, to be honest.
more of a semi-retired. You gotta realize, of course, that I have also other passions that have nothing to do with science.
I mean, as you should. I'm sure you're a very curious person.
I'm a lover of
cannot stop.
I'm the lover of the blues, and there's certainly rock and roll. And I'm one of the biggest fans of the Rolling Stones. So
it's the favorite band of my father. Oh,
that is
okay,
the same ring that's the same ring that Keith Richards wears. You know who Keith Richards is?
I know it's not his ring. It's the same though, right?
Yeah, it's not his ring. It's the same. It's
okay.
made by the same person. But you know who he is, right?
Everybody knows Keith Richards. What do you mean? Yeah, for a second I was about to like pass out because I thought this was his actual ring that you were wearing.
But it's the same. It's the same.
It's extremely similar though. Yes. It's still scary. It's still scary. There's a lot of depth in your life, Dr.
Well, I've seen the Rolling Stones live. I've seen the Rolling Stones live 17 times. Starting in 1967 in Athens, a few days before the junta took over. That was the 67 in April 1967. The second time was in July 3rd in Hyde Park. Your Hyde Park.
Yeah, of course.
Shortly after Brian Jones died, and they had a free concert in Hyde Park. I was there. And then the rest of the time was mostly in the US. So
I mean, I'm sure that if I was able to like be there in the US, in the era you grew up, I mean, I don't know. I grew up in a very, very different era. I was born in 1997. So the only way for us young guys and girls to know how it was is through people like you. I mean, I can imagine how you felt going to a Rolling Stones concert. But
yes.
Can I really? No, I cannot do that through videos. And it's not the same.
I remember it was an interesting time. It was an interesting.
There's like no phones. People are having fun. You don't need to message someone. You call them on the old dial phones. You go out. You meet people. You don't sit all day. I mean, technology helps. Look at this interview. It helps. Okay, but we use it for not good causes. I believe it was a better period back then.
Well, I mean, every period has
for people.
I mean, I don't.
Yes.
Don't want to be critical. To me, there were many things that were when I was, especially when you're young, of course, it makes a big difference. And we were, I would say, we're very, very lucky in a sense that if just a couple of decades before that time, we would have been people that were, suffered from the war and so on. Instead, we were the beneficiaries of an advance. An advance was very peaceful in many ways. If you want to put aside some of the unfortunate adventures we tried to do here in this country with Vietnam, everything needs to be populated. I've got all my notes and all my. I still have a big job to do in terms of collecting all my notes and unpacking all the boxes of books and so on.
I mean, it's incredible that you are in your 70s now and you are still working.
I'm going to be 76.
You don't want to. Yeah, you're going to be 76. You were born in 47, so it's incredible that you don't want to stop and you have this energy. You have the energy of a young guy. You don't have the energy of a person who's 76.
I don't have the energy of a young guy, but I still have the drive.
Okay, maybe not 100%, but I can see that that keeps you alive. It keeps you bright and alive. How you're working on something you love, and I think it's a paradigm for us, for the young generation.
Well, they say, they tell you that exercising the brain is one way to avoid dementia. I think we are facing a major problem with people in terms of dementia, and some of that you can't fix it all. You can't avoid it. It's particularly the acute cases. But at least the evidence shows that if you practice it, you can delay it. And I try very hard to stay up in terms of reading and connecting and also speaking to people like you. So I don't just do it to be helpful. I do it because it also helps my brain. But
if I'm able to even remotely offer you a little bit of help, Dr. Patrinos, it's an honor. What can I say? And I'm very glad we had this conversation. Like I certainly learned a lot, and information I wouldn't be able to find access to without talking to a person like you. And thank you so much. I will be in touch with a finalized interview in 2 weeks, about 2 weeks.
Have a good time. Take care of yourself. Bye-bye.
You too. Thank you again. Bye. Bye.